So let's start the first lecture after second lockdown. So already we have seen definition of convergent sequence, divergent sequence, then some operations on convergent sequence. Then we have seen monotone sequences. So in offline mode, so already we have seen all this part. So let's start. Next topic, that is limit superior and limit inferior. So this is our lecture number 35, online plus offline. So in this lecture, this is MAT-501 actually. So it is MAT 501. So it is there. So what is the definition of limit superior? So let the sequence Sn be sequence of real numbers that is bounded above, and let Mn equal to least upper bound of this set, that is Sn plus 1, Sn plus 2 up to infinity. So then first, if sequence Mn converges, then we define limit superior of Sn as the n tends to infinity will be limit of the sequence Mn, capital Mn. So what is capital Mn? It is defined as least upper bound of this set Sn plus 1 up to infinity, where Sn is sequence of real numbers and that is bounded of the sequence. So B, if sequence Mn diverges to minus infinity, so this sequence Mn is monotonic decreasing sequence, and if it is not bounded below, so naturally it will diverge to minus infinity. So in that case, we'll write limit superior of Sn as n tends to infinity will be minus infinity. Actually, it is equal to minus infinity. So this is the definition of limit superior. What is the definition of limit inferior? See, let Sn be sequence of real numbers that is bounded below, and let small mn, that is greatest lower bound of the set Sn plus 1 up to infinity. Then limit inferior of Sn is nothing but limit of the sequence Mn, small mn, as n tends to infinity, if sequence Mn converges. So naturally, if sequence Mn converges, then its limit exists. Then that limit will be limit inferior of the sequence Sn. So this is first case. If sequence Mn, small mn, diverges to plus infinity, actually this sequence Mn, small mn, is monotonic increasing sequence, and if it is not bounded above, so in that case, so the sequence will diverge to plus infinity and will define. So limit inferior of sequence Sn will be plus infinity. So let us consider some remarks. If sequence Sn is sequence of real numbers that is not bounded below, so in that case we write limit inferior of sequence Sn will be minus infinity. And second, see, if sequence Sn is convergent sequence of real numbers, then limit inferior of Sn as n tends to infinity, so will be limit of that sequence Sn. If sequence Sn itself is convergent, then its limit inferior will be limit of that sequence. So for example, if you consider sequence minus 1 raised to n, then what will be its limit superior and what will be its limit inferior? So naturally, limit superior of the sequence minus 1 raised to n will be 1 and limit inferior will be minus 1. So manually, you can use this definition to find limit superior and limit inferior of this sequence. So you can do it. You can observe directly. So limit superior is nothing but plus 1 and limit inferior is nothing but minus 1. So there are some properties of limit superior and limit inferior. So let us see one by one. So first, if sequence Sn is sequence of real numbers, then limit inferior is always less than or equal to limit superior of Sn. It is always true, because limit inferior is nothing but greatest lower bound and limit superior is nothing but least upper bound. So naturally, so this relation, so this inequality will be always there. So let's see. Second, if sequence Sn is sequence of real numbers and if limit superior is equal to limit inferior, and that is equal to suppose L. So both values, limit superior and limit inferior, are equal and that equal value is capital N. So in that case, this equal value is nothing but limit of the sequence Sn. Let us see, if limit superior and limit inferior both are same, then that equal value is nothing but limit of that sequence Sn. So this is another property. So next, if Sn and Tn are two bounded sequences of real numbers and these two sequences satisfy this relation, that is, each term of sequence Sn less than equal to corresponding term of Tn, and it is true for all n. It means that S1 greater than less than equal to T1, S2 less than equal to T2, and likewise. If this relation is there and both the sequences are bounded sequences of real numbers, so in that case, see, limit superior of Sn will be always less than equal to limit superior of Tn, and limit inferior of the sequence Sn will be always less than equal to limit inferior of sequence Tn. So these two relations will be there. These are theorems. So we are skipping proofs of all this research. Just we are stating these as properties of limit superior and limit inferior. So next, if Sn and Tn are bounded sequences of real numbers, then limit superior of Sn plus Tn always less than equal to limit superior of Sn plus limit superior of Tn, and second, limit inferior of Sn plus Tn greater than equal to limit inferior of Sn plus limit inferior of Tn. So this is second property and this is first property. So what is limit superior of addition of two sequences? So this relation will be there. Next theorem actually is property of bounded sequences. So let us see, any bounded sequence of real numbers has convergent subsequence. See, so this is very important theorem, that is Bolzano-Weierstrass theorem. See, so this theorem is nothing but Bolzano-Weierstrass theorem. So I'm putting box for it because it is very important. It may be asked in objective question. So what is statement of Bolzano-Weierstrass theorem? Let us see. See, Bolzano-Weierstrass theorem. Any bounded sequence of real numbers has always convergent subsequence. Any bounded sequence of real numbers always have convergent subsequence. Any bounded sequence of real numbers has convergent subsequence. So this is statement of Bolzano-Weierstrass theorem. So famous theorem, its proof is there. So obviously, so we are skipping proof of this theorem. If statement is important, it may be asked in objective questions, or so this property of bounded sequence. So next, so see, so these are some examples. So you can do it at home. Find the limit superior and limit inferior of the sequence 1, 2, 3, 1, 2, 3, and likewise. So 1, 2, 3, 1, 2, 3. So this sequence is 1, 2, 3, 1, 2, 3, 1, 2, 3. So this pattern is going to repeat infinitely. So what will be limit superior and limit inferior of the sequence? So you can check and you can observe. So limit superior, so limit inferior of the sequence will be 1, and limit superior of the sequence will be obviously 3. So it is there. And for this sequence, you can find limit superior and limit inferior also. So this is second example. So next topic, that is Cauchy sequence. What is the definition of Cauchy sequence? A sequence Sn of real numbers is said to be Cauchy sequence if for every epsilon strictly greater than 0 there exists positive integer n0. For every epsilon strictly greater than 0 there exists positive integer n0 such that it should satisfy this condition, that is mod of Sn minus Sm should be strictly less than epsilon for all n m greater than equal to n0. So whenever small m are greater than equal to n0. N0 is fixed positive integer. For given epsilon is greater than 0, there exists fixed positive integer n0, so that it should satisfy this condition. So whenever n m greater than equal to n0, so you'll always get mod of Sn minus Sm strict less than epsilon. That is, whenever nm greater than equal to n0, mod Sn minus Sm should be strict less than epsilon. It should be true for every epsilon. So epsilon may be very very large or epsilon may be very very small. So you can take epsilon very small, still you will get distance between nth term and m term of the sequence will be strict less than epsilon. So this is the definition of Cauchy sequence. So there are certain properties of this Cauchy sequence. Every convergent sequence of real numbers is Cauchy sequence. Means every convergent sequence is always Cauchy sequence. Every convergent sequence is Cauchy sequence. Second property, if Sn is Cauchy sequence of real numbers, then it is bounded. Every Cauchy sequence is bounded sequence. So that is second property. What is third property? If Sn is Cauchy sequence of real numbers, then it is convergent. Means every Cauchy sequence of real numbers, every Cauchy sequence of real numbers is convergent. Every Cauchy sequence is convergent. What is first property? So we can see shortlist these properties. These three properties. Every convergent sequence is Cauchy sequence. Cauchy sequence is always bounded sequence. Cauchy sequence is always convergent sequence. Cauchy sequence of real numbers is convergent sequence. So that is third theorem. So there is remark. See, if Sn is Cauchy sequence of real numbers which has subsequence converges to L, then sequence Sn itself converges to L. So what is statement of this remark? Let us see. If Sn is Cauchy sequence of real numbers which has subsequence converges to L, means one subsequence of Cauchy sequence Sn converges to L, then Cauchy sequence Sn itself converges to L. Means if one subsequence of Cauchy sequence converges to limit suppose L, then Cauchy sequence itself also converges to that limit L. So that is another property and we write it as a remark. Let's see. So exercise. So show that sequence 1 upon n is Cauchy sequence. So you can take uh, small m greater than equal to n0. So you will always get, so mod of 1 upon n minus mod of 1 upon m will be less than epsilon for all n m greater than equal to n0. So this sequence is Cauchy sequence. Also you can observe that 1 plus 1 upon n raised to n varies from 1 to infinity is Cauchy sequence. So why these two sequences are Cauchy sequence? Just we have seen every convergent sequence is Cauchy sequence, and already we have seen 1 upon n is convergent sequence and 1 plus 1 upon n raised to n is convergent sequence, and therefore these two sequences will be Cauchy sequence. So there are some multiple choice questions on the chapter, that is real sequences. So let us see first question. Every convergent sequence is bounded. See, every convergent sequence is, so options are, see, bounded, unbounded, oscillates, none of these. So naturally, if sequence Sn is convergent sequence, so naturally it will be bounded sequence. This sequence minus 1 raised to n, see, options are, it is convergent, obviously it is not convergent, not bounded, none of these. So naturally minus 1 raised to n, each term of the sequence is either 1 or minus 1. So naturally it is bounded sequence. Bounded below by minus 1 and bounded above by plus 1. So this is bounded sequence. So you can check. This sequence is bounded sequence. Sequence 1 plus 1 upon n raised to, so actually it is 1 upon n raised to n varies from 1 to infinity. So it is a well-known sequence. This sequence converges to E. So this is option of this objective. So naturally next question, the sequence 1 1 1, which is constant sequence. So every constant sequence is convergent, so naturally the sequence is convergent. Next, minus 1 raised to n into n. So this sequence is oscillatory sequence. This sequence is not convergent, not bounded. So naturally it is oscillator sequence. You can observe. So these are the, yes, correct options of these objectives. Next, the sequence 1 plus 3 upon e raised to e. N varies from 1 to infinity converges to. So already there is one result. See, 1 plus 2 upon n e, sorry, it should be n, not e. So sequence 1 plus 3 upon n raised to n varies from 1 to infinity. So this sequence converges to e cube. If you take 2 instead of 3, so then the sequence converges to e square. This. If you take 1, then this sequence converges to e. So this is correct option. Every bounded sequence is, so this is statement of Bolzano-Weierstrass theorem. Bolzano-Weierstrass theorem. So this is statement of Bolzano-Weierstrass theorem. Every bounded sequence has a convergent subsequence. Just we seen. So this end of the chapter, that is chapter real sequences. So next chapter, that is chapter 3, and it is series of real numbers. See. So what is the definition of infinite series of real numbers? If n is a sequence of real numbers, then summation an a1 plus a2 plus a3 plus goes to infinity is called infinite series of real numbers. Means if we add all terms of the sequence, then resulting series is called series of real numbers. Infinite series of real numbers. So this is series of real numbers, means it is summation of terms of the sequence, and it is infinite summation, therefore it is called infinite series of real numbers. See, so next, what is sequence of partial sums of given series? If summation an is infinite series, then the sequence Sn, so it is capital Sn, n varies from 1 to infinity, is called sequence of partial sum. See, sequence of partial sum of series summation an, where what is Sn? So Sn equal to a1 plus a2 plus up to plus an. So the sequence Sn is called sequence of partial sum of series summation an. So remark, you can observe that. Let us see. What is S1? S1 will be A1. S2 will be A1 plus A2. So what are the terms of the sequence Sn? So the sequence will look like this. That is, second term will be A1 plus A2. Third term will be A1 plus A2 plus A3. Fourth term will be A1 plus A2 plus A3 plus A4, and likewise n term and all remaining terms you can see. So n term will be addition of first n terms of the sequence an. So what is convergent series? So it is very important. When we say, so given series is convergent, an infinite series summation an is said to be convergent if the sequence Sn of its partial sum is convergent. So if the sequence Sn is convergent, then corresponding series is convergent. So convergence of series is nothing but convergence of sequence. So you can observe, if the sequence Sn converges to A, then we say that the series summation an converges to A, and in this case we write summation an equal to capital A. Means if sequence Sn converges to capital A, so in that case that series also converges to capital A, and we'll write summation of the series is nothing but this capital A. So let us see. So what is summation of series? Summation of series an is nothing but limit of sequence of its partial sum. So there are some theorems on series. So first, if summation an converges to capital A, and summation bn converges to capital B, then summation an plus bn also converges to a plus b. So this one property, that is what is the addition of two series, convergent series. So naturally n plus bn also converges to a plus b. So next, what is necessary condition for convergence of the series? See, if series an converges, then limit of an equal to 0. Means if the series summation an is convergent series, then limit of the sequence an is always 0. So converse part of this theorem is not true. And there is one counter example for that. So we can write converse is not true because summation 1 upon n varies from 1 to infinity, is divergent series. But limit of the sequence an as n tends to infinity is 0. Means it is not necessary. If limit of an is 0, then it does not, see, it does not imply that so corresponding series is convergent. But surely if series is convergent, then limit of the sequence n is convergent. So for convergence, you can check if limit n is not equal to 0, so surely that series will be not convergent. So that is necessary condition but not sufficient condition. So next examples. So you can check series summation 1 upon n into n plus 1. So this series converges to 1. Summation 1 upon n plus 1 into n plus 2 converges to half. Summation n plus 1 divided by n plus 2. So this series is divergent series. See, summation n plus 1 divided by 10 raised to 10 into n plus 2. So again this series is divergent series. So summation log 1 plus n. So this series is divergent series. So summation cos 1 upon n square. So this series also divergent. So all these solutions are available in book. If you are interested, you can see. So summation 1 upon n. So this series is divergent series. But summation 1 upon n square. This series is convergent series. See. So there is one remark. Actually, there are two remarks. Let us see. First, if summation an converges, so first series is convergent series, and the second series is divergent series. Then summation an plus bn means series of addition of these two series, summation an and summation bn. First is convergent, second is divergent. Then resulting series, that is series of summation, so will be divergent series. So this first remark. Second remark, this series summation 1 upon n raised to p is convergent for some values of p and some values of, sorry, so there should be p, not n. So let us see. If p is strictly greater than 1, then summation 1 upon n raised to p. So this series will be convergent. And if p less than equal to 1, then this series is divergent. It means that for p equal to 1, this series is divergent. For p equal to minus 1, this series is divergent, and likewise. But if p is strictly greater than 1, means if you take p equal to 3, 2, or 3 or 4, then resulting series will be convergent. So this series is called p series, np series actually. And this is nothing but, so this theorem, actually this theorem is called convergence of p series. For which values of p this series is convergent, and for which values of p this series is divergent. So surely if p is less than or equal to 1, then this series is divergent, and for p is greater than 1, this series is convergent. You can see it. So this series is called NP series and its convergence. So series, next theorem, that is series with non-negative terms. Actually it is theorem. So what is statement of this theorem? Let us see. if summation an is series with non-negative terms with Sn equal to a1 plus a2 plus up to plus an. So where n is positive integer, then see summation an converges if the sequence Sn is bounded. If the sequence Sn is bounded, then this series converges, and the sequence Sn is not bounded, then this series diverges. So this is series with non-negative terms, means each term of the series is either positive or zero. Surely. So this statement of this theorem. So this sequence is monotonic increasing sequence. If the sequence is bounded above, then this sequence will be convergent, and therefore this series will be convergent because it is sequence of partial sum of this series. So obviously, next, that is convergence of geometric series. So summation x raised to n, this series is called geometric series, and here x is common ratio. So if you write term wise this series, it will be, so if you take n equal to 1, so actually you can take n equal to 0 also, no matter. So if n equal to 1, so this will be x plus x square plus x cube plus, and it goes to infinity. So this is geometric series with common ratio x. So for which values of x this series is convergent, and for which values of x this series is divergent. So this theorem is nothing but convergence of geometric series. So for x strictly lies between 0 and 1, means if x lies between 0 and 1, then this series converges to 1 upon 1 minus x. And if x strictly greater than 1 or greater than equal to 1, then this series summation x raised to n diverges. Means geometric series converges for x lies between 0 and 1, and this that converges to 1 upon 1 minus x in that case. And if x greater than equal to 1, if x equal to 1 or greater than equal to 1, then this series diverges. So this is statement of this theorem. So there are some examples, you can see solutions for these examples which are available in book. If you are interested, you can check. So first, that is summation. So you can write this series as summation 1 upon n factorial. So here n varies from 1 to infinity. So this series is convergent series. Summation 1 upon n is divergent. Summation 1 upon n factorial is convergent. Summation 1 upon 2 raised to n is convergent. So here you can take x equal to half in geometric series. So obviously it will be convergent. If you take, see, x equal to 1 upon 3 in geometric series, then this series will be convergent series because 1 upon 3 lies between 0 and 1. And similarly, if you take x equal to 3, then this series will be divergent because x is strictly greater than 1. So obviously this series will be a divergent series because of convergence of geometric series. So next theorem or next type of series, it is alternating series. So what is alternating series? Let us see. Means alternate terms are positive, negative, positive, negative. Such type of series is called alternating series. So if n varies from 1 to infinity is sequence of positive numbers such that a1 greater than equal to a2, a2 greater than equal to a3, a3 greater than equal to a4, likewise an greater than equal to n plus 1 and greater than equal to n plus 2, and so on. Means this sequence a1 is decreasing monotonic, non-increasing means it is decreasing sequence, and limit of sequence an as n tends to infinity equal to 0, then the alternating series minus 1 raised to n into an. So what are the terms of the series? You can see first term, if you take n equal to 1, so minus a1 plus a2 minus a3 plus a4 minus a5 plus, and so on. So this is alternating series. So minus plus minus plus. So alternate terms are positive negative, and that's why the series is called alternating series. So this series is convergent. When this series is convergent, see, if this sequence n is monotonic decreasing sequence and its limit is 0, then corresponding alternating series summation minus 1 raised to n an is convergent. So from that you can check. So summation minus 1 to n 1 upon n, this series is convergent, but summation 1 upon n varies from 1 to infinity. So this series is divergent. This series is not convergent, but this its corresponding alternating series is convergent. And similarly, you can check here for n into minus 1 to n plus 1 divided by 2n minus 1. So this series is a divergent series. So next type of convergence, that is conditional convergence and absolute convergence of infinite series. So let's see what is definition of conditional convergence and absolute convergence. So definition of conditional convergence, definition of conditional convergence and yeah, absolute convergence. See, so let summation an be a series of real numbers. So first, if summation of mod n means yes series of mod n converges, we say that summation an converges absolutely. So when we say summation converges absolutely, if it's series of, see, its mod series means summation mod an converges. If you take mod of each term of this series, then corresponding series is convergent. Then we can say original series converges absolutely. Actually, there is one theorem. If series converges absolutely, then that series also converges. Means here it does not mean that summation an converges. If summation mod an converges, then we say that summation an converges absolutely. Means series of absolute terms of given series converges, then we can say given series converges absolutely. So this is absolute convergence. What is conditional convergence? If summation converges but summation mod an diverges. If summation mod an diverges but summation an converges, so in that case we can say that summation an converges conditionally. So this is conditional convergence. What is absolute convergence? Absolute. See, in absolute, summation mod an is convergent. Implies that summation an converges absolutely. What is conditional convergence? Summation an convergent. So in absolute convergence, both series, summation mod an as well as summation an convergent. In conditional convergence, summation summation mod an is divergent and summation an is convergent, then it is conditional convergence. In conditional convergence, only summation n is convergent. Summation mod n is not convergent. In absolute convergence, both series summation mod an as well as summation an are convergent. So then it is absolute convergence. So this is conditional convergence and this is absolute convergence. In absolute convergence, both series summation mod an as well as summation an are convergent. In conditional convergence, only summation an converges. Summation mod an does not converge. Then corresponding convergence is called conditional convergence. So you can check the series 1 minus 1.2 plus 1.4 plus minus 1.8. This series converges absolutely, because if you take, see, series of mod terms, so you'll get this series, that is summation 1.2n, and this series is convergent series. So both. So this series as well as series of its absolute or absolute series or series of mods. So both series converges. Also this series 1 minus half plus 1.3 minus 1.4 plus and likewise. So this series converges conditionally, because so summation mod of this series means, so this series will be summation 1 upon n and this series is divergent, and therefore this series means original series is convergent, but its series of mods or absolute terms is not convergent, and therefore this series convergence conditionally. So it is there. So there is one theorem. If summation an converges absolutely, then summation an converges. So it is same thing. Means what is absolute convergence? Means summation mod an is convergent, and this theorem tells that if summation mod an is convergent, implies that summation an also convergent. Means in absolute convergence, both series summation mod an as well as summation an convergent. But in conditional convergence, only this series is convergent, this series is not convergent. So separation of series. See, we will separate given series in series with positive terms and series with negative terms. So let summation n be given series. We separate this series with the series with positive terms and series with negative terms. See, let summation n be the series of real numbers. So let capital Pn. What is capital Pn? It is n if n greater than equal to 0. Means Pn, it is phi n equal to an if an is either 0 or greater than equal to strictly greater than 0, and this is 0 if n is negative. Means if, see, if term of series is positive, then that will be term of Pn, and if it is negative, then so instead of that term we will take 0. Means we are taking only positive terms in Pn. And what is Qn? So Qn equal to 0 if n is positive, and n equal to, sorry, Qn equal to n if an less than equal to 0. Means if n is negative or 0, so corresponding term we will take in Qn. So alternately, for example, let us say for the series we can take 1 minus half plus 1 upon 3 minus 1 upon 4 plus goes to infinity. So what is P1? P1 equal to 1, P3 equal to 1 by 3, P5 equal to 1 upon 5. So we are considering only positive terms in P series. So first term 1, second 1 upon 3, 1 upon 5, and likewise. And negative terms. Obviously, you can observe here. See, means first term is 1. Second term, which is negative, and that's why we are taking it as 0. So P2 equal to 0. P3, which is positive, so we will take it as P4, which is negative, so instead of that negative term, we will take it as 0. P5 is positive, so we'll take that term. P6 is negative term, so instead of that term, we'll take it as 0 and likewise. See, so what is P series? P series will be 1, 0, 1 upon 3, 0. So 1 plus 0 plus 1 upon 3 plus 0 plus 1 upon 5 and likewise. Means it contains only positive terms. And what is Q series? So Q1 will be 0 because it is positive term, Q2 is negative term, so we will take it as it is. Q3 is 0, Q4 minus 1 upon 4 and likewise. So you can observe. So for this example, what is P series and what is Q series? So summation Pn, that is series with positive terms, and Qn, that is series with negative terms. So it can be observed that Pn equal to maximum of An and 0, and Qn, that is minimum of An and 0. So using formula of maximum and minimum, so Pn will be An plus mod An divided by 2, and Qn, that is An minus mod An divided by 2. So it gives that. So if we add these two, Pn plus Qn, you will get An. Let us see. So if we add Pn and Qn, so you will get An. So this is separation of given series. Means summation An is separated into series. See, summation An, we write it as summation Pn plus summation Qn. This is separation of series. We separate Yeah. So we separate given series in addition of two series. We separate given series in series of positive terms and series of negative terms. So next there is theorem. If summation n converges absolutely, then summation both series summation pn is less summation qn converges. And second, if summation converges absolutely, summation an converges absolutely, then both summation Pn and summation Qn converges. That is first. Second, if summation An converges conditionally, then both summation Pn and summation Qn diverges. So next, there are tests for absolute convergence. So first test. So before that, there is one definition that is dominated by. So let summation An and summation Bn be two series of real numbers. Then summation An is said to be dominated by summation Bn if there exists positive integer n0 such that mod an less than equal to mod bn for all n greater than equal to n0. So whenever n greater than equal to n0, mod of an less than equal to mod bn. So it may not satisfy this inequality for first n0 terms, means it may not satisfy this condition for finite terms. So instead of that finite terms, it satisfies this inequality for infinite number of terms. So in that case, we will say that summation an is dominated by summation bn. So when we say summation n is dominated by summation bn, so there exists fixed positive integer n0 such that mod of an less than equal to mod bn for all n greater than equal to n0. See, so in this case, we write summation an is dominated by summation bn. So this notation stands for dominated by. So dominated by. So meaning of this notation, summation an is dominated by summation bn. So for example, you can observe summation minus 1 raised to n divided by n square is dominated by summation 1 to n plus 1. Because mod of minus 1 raised to n divided by n square is less than 1 to n plus 1 for all n greater than equal to 3. So you can take n0 equal to 3 here, or you can take 4. So whenever n greater than equal to 4, so you'll get this inequality, and therefore first series is dominated by second series. So first test for absolute convergence, and that is comparison test. So first test is comparison test. So we'll just state this theorems. So first, if summation n is dominated by summation bn, and if summation bn converges, means summation n is dominated by summation bn, means summation bn is larger series and summation n is smaller series. If yes, bigger series converges absolutely, then smaller series like summation en also converges absolutely. If summation n is dominated by summation bn, and if summation bn converges absolutely, then summation n also converges absolutely. If summation n is dominated by summation bn and summation mod an diverges infinitely, diverges to infinity, then summation mod bn also diverges to infinity. See, so this is comparison test. Means you are comparing two series. If bigger series converges, then smaller series also converges. If smaller series diverges, then bigger series also diverges. So this is comparison test. So next test, that is limit test. If summation bn converges absolutely, and if limit of mod n divided by mod bn exists, then summation en also converges absolutely. So if summation bn converges absolutely, and if this limit exists, then directly you can say second series, that is summation en also converges absolutely. See, so this is limit test. And if see summation mod an is divergent, and if this limit exists, then we say that summation bn also diverges. If summation mod an diverges, then summation mod bn also diverges if this limit exists. See, the value of this limit is finite, then In that case, if one series, that is summation an diverges, then second series summation bn also diverges. And if second series converges, then first series also converges. So this is limit test. So one of these two series, so from one convergence of one series, you will get convergence of second series, or convergence of divergence of first series, you will get divergence of second series. This is limit test. So next, that is ratio test. This test also called as D'Alembert's ratio test. D'Alembert's ratio test. So let summation an be series of non-zero real numbers, and let small a equal to limit infimum of limit in infimum of mod n plus 1 divided by an as n tends to infinity, and capital An, that is limit superior of mod n plus 1 upon an. So then if mod a is less than 1, then summation mod an is convergent, and if small a is greater than 1, then summation mod an diverges. And if small a less than equal to 1 and capital A greater than equal to 1, so then this test fails. So we can write alternate form of this series. So instead of limit superior and limit inferior, so we can take C. So what is alternate form of this series? Sorry, test. That is ratio test. Light. So limit mod an plus 1 divided by an equal to L. So from that, see, if value of this limit is less than 1, then resulting series converges. If L is greater than 1, then resulting series diverges. And if L equal to 1, so you cannot predict anything. Means this test fails in that case. So this is ratio test. So ratio means you are taking ratio of n plus 1 divided by n. So if value of this limit strictly less than 1, so resulting series converges. If it is strictly greater than 1, then resulting series diverges, and this test fails if value of this limit of ratio is 1, then this test fails. So next, that is root test. So let actually this test is also called Cauchy's-Yang root test. See, let summation a and b series of non-zero real numbers, and let limit of n raised to 1 upon n is equal to L. Then this series is convergent if L is less than 1. If L is greater than 1, then this series diverges. And if L equal to 1, then this test fails like previous test. So these are some tests to check with the convergence of infinite series. Absolute convergence of infinite series. So here, these are some examples. You can use this test to check convergence of the series. So first, that is 1 plus 1 upon n raised to 2n divided by e raised to n. So you can use here a ratio test. You can use a ratio test to directly get convergence of the series. So here, so you have to use comparison test. So given series you can write in the form. So this series is, you'll write in the form that is summation n divided by 2n minus 1 into 2n plus 1, and you can take another series. So you have to choose this series. So you can choose bn equal to 1 upon 6n. So in that case, see, so using comparison test, so 1 upon 6n. So this series, see, is greater than 1 upon 6n. So 1 upon 6n is a divergent series, and therefore this series will be divergent. So you can check divergence of the series. Similarly, same, you will use comparison test to to check convergence of summation. So this series, that is summation n into n plus 1 divided by n plus 2 into n plus 3 into n plus 4. And you will choose another series n equal to 1 upon n, and sorry, you are using limit test, not comparison test. So limit of n upon bn equal to 1 which exists, see, and therefore both series converges or diverges. Since an diverges, therefore original series diverges using limit test. So n raised to n upon n factorial. So here again you are using ratio test. So you'll check convergence. So limit is greater than 2 and therefore this series is divergent. N factorial upon n raised to n. Again you are using comparison test. Limit is half strictly less than half, which is strictly less than 1, and therefore this series is convergent. So these are some multiple choice questions. You can check summation 1 upon n varies from 1 to 1, 1 to infinity. So this series is divergent. Summation n is said to be absolutely convergent if see, limit n equal to 0, limit n equal is positive, n is divergent, summation mod n is convergent. So obviously, so this option is correct. A series with terms are series whose terms are absolutely positive and negative is called, obviously it's not oscillating series, but it should be alternating series. Alternating series. If for a series summation an limit n equal to 0, then the series summation n is convergent. Obviously, yeah. Obviously, this is the converse of that theorem just we have seen. So if summation an is convergent, it implies that limit n tends to infinity is equal to 0. Means if series is convergent, then this limit is 0. But if limit is 0, then it does not implies that series is convergent. So it need not be convergent. So convergence is not true of this theorem. Obviously, if summation an converges to a and summation bn converges to b, then summation n plus bn converges to a plus b. So again, it is one statement of theorem. This is convergence of NP series. It is also called hyperharmonic series. Or it is called NP series. See? So for p is greater than 1, then this series is convergent. For p less than or equal to 1, then this series is divergent. If summation n converges absolutely, then the series summation an is. So this is the definition of conditional convergence. Then summation an is divergent. So obviously it is divergent. If the series summation mod n converges, then the series summation an converges. Yes, it converges. That is, absolute convergence implies convergence. So this is the end of this chapter. Series, infinite series. So last chapter, that is chapter 4, and that is Jacobians. So we'll see. First definition of Jacobian. What is Jacobian? If mu1, u1, u2 up to un are functions of n variables, x1, x2 up to xn, then the determinant, let us see, determinant dou u1 if u1, u2 up to un are functions of n variables x1, x2 up to xn, then the determinant. So this determinant, which is n cross n determinant, let us see, dou u1 by dou x1, dou u1 by dou x2 up to dou u1 by dou x1, xn, dou u2. So this first row, let's see. What is second row? What is second row? That is dou u2 by dou x1, dou u2 by dou x2 up to dou u2 by dou xn. And this is row n, that is nth row. Dou u1 by dou x1, dou un by dou x2 up to dou n by dou xn. So this determinant is called Jacobian of u1, u2 up to un with respect to independent variables x1, x2 up to xn. And it is denoted by, so these are some notations for this determinant, and actually it is Jacobian, sorry. So Jacobian of u1, u2 up to un with respect to x1, x2 up to xn. So this first notation, or it can also be denoted by this notation, that is capital J of u1, u2 up to un. Or so this notation is rarely used. We are not using this notation. We'll use this notation only. Also, we'll not use this notation, or rarely we'll use it. So remark: if the functions u1, u2 up to un are of the form, so u1 is just function of x1, u2 is function of x1 and x2, u3 is function of x1, x2, x3, see, and un is function of x1, x2 up to xn. So similarly, you'll write un minus 1 is a function of, see, it is just function of x1, x2 up to xn minus 1. Means xn is not there. Then what is Jacobian of u1, u2 up to un with respect to x1, x2 up to xn? So this is nothing but determinant of this. See, so what is value of this determinant? You can check the value of this determinant is nothing but it is just multiplication of diagonal entries. So basically it will be dou u1 divided by dou x1 into dou u2 by dou x2 into up to, it will be dou un divided by dou xn. See, this will be determinant Jacobian of u1, u2 up to un with respect to x1, x2 up to xn. So there are some examples. So directly you can use the definition of Jacobian and you will find, see, value of this Jacobian, it will be r square into sine theta. So you can do it at home. So homework, just try to check. Similarly, so this second, if y1 is function of x1, y2 is function of x1, x2, and similarly yn is function of x1, x2 up to xn. So you have to use that remark. So using that remark, you'll directly get the value of Jacobian equal to this. If u is equal to y square upon 2x equal to x square plus y square upon 2x, then what is value of this Jacobian? So again, just you have to use definition of Jacobian, you will find, so this is nothing but minus y upon 2x. So there are some cases or some specific situations, see, of functions to find Jacobian. So first theorem, actually first case, that is case of functions of functions. If u1, u2 up to un are functions of, let us see, y1, y2 up to yn, and y1, y2 up to yn are again functions of x1, x2 up to xn. So in that case, what is Jacobian of u1, u2 up to un with respect to x1, x2 up to xn? So this is nothing but, so multiplication of these two Jacobians. So this is one Jacobian and this is second Jacobian. So first, it is Jacobian of u1, u2 up to un with respect to y1, y2 up to yn, and again second Jacobian, it is nothing but y1, y2 up to yn with respect to x1, x2 up to xn. See, so there is another theorem, that is so multiplication of these two Jacobians is always 1. You can observe it. Jacobian of y1, y2 up to yn with respect to x1, x2 up to xn, and Jacobian of x1, x2 up to xn with respect to y1, y2 up to yn is equal to 1. So maybe it will ask in objective question, MCQ. See, so next, Jacobian of implicit functions. So what is implicit function? Let us see. If u1, u2 up to un are, instead of being given explicitly in terms of x1, x2 up to xn, be connected with them by equations such as, means u1, u2, un are not directly functions of x1, x2 up to xn, but these are connected by other functions or connected by some function. So suppose capital F1 is a function of u1 u2 up to un x1 x2 up to xn equal to 0. Capital F2 is a function of u1 u2 up to un x1 x2 up to xn, and similarly Fn is a function of u1 u2 up to un x1 x2 up to xn equal to 0. So these relations are there between these functions. So in this case, u1 u2 up to un may be regarded as implicit functions of x1 x2 up to xn. Means directly it is not given that u1 u2 up to un are functions of x1 x2 up to xn, but these are connected by some relations. See, so such type of functions are called implicit functions. If u1 u2 up to un are implicit functions of x1 x2 up to xn, then see statement of the theorem. Jacobian of capital F1 F2 up to Fn with respect to u1 u2 up to un into, see, so Jacobian of your capital F1 F2 up to capital Fn with respect to u1 u2 up to un into Jacobian of u1 u2 up to un with respect to x1 x2 up to xn. So this is equal to minus 1 raised to n Jacobian of capital F1 F2 up to Fn with respect to x1 x2 up to xn. See, so necessary and sufficient condition for Jacobian to vanish. So when Jacobian vanishes, what is necessary and sufficient condition for that? If u1 u2 up to un be functions of n independent variables x1 x2 up to xn, then u1 u2 up to un are independent. So in that case, u1 u2 up to un are dependent variables, and so when we say u1 u2 up to are dependent, if and only if their Jacobian vanishes. See, u1 u2 up to un are functions of n independent variables x1 up to xn. Then if Jacobian is 0, then we say that u1 u2 up to un are dependent variables, or if u1 u2 up to un are dependent variables, then directly we will say that so their Jacobian will be 0. That is Jacobian u1 u2 up to un with respect to x1 x2 up to xn 0. So this end of the chapter, that is Jacobian. So there are some multiple choice questions. You can check. If u is equal to x plus y minus z, v equal to x minus y plus z, and w equal to x square plus y square plus z square minus 2iz, then what is Jacobian of uwz with respect to xyz? You have to use just definition of Jacobian, directly you will find, and this is equal to 0. Just you have to use these definitions of Jacobian. So these are some MCQ. The second, yeah, is there. If u1 u2 up to un are functions of n independent variables x1 x2 up to xn, and if capital F of u1 u2 up to un equal to 0, then what is Jacobian of u1 u2 up to un with respect to x1 x2 up to xn? See, obviously that is equal to 0, just as in one theorem. Next, if x equal to r cos theta, y equal to r sin theta, then what is Jacobian of xy with respect to r theta? Obviously it is r. Then what is product of Jacobian of u1 u2 up to un with respect to y1 y2 up to yn, and Jacobian of y1 y2 up to yn with respect to u1 u2 up to un. So if we take product of these two Jacobians, then obviously that is 1. So just we stated one property of Jacobian, and this end. So this end of the chapter Jacobian, and this end of this course real analysis. So best luck for your objective examination, for online examination. See, so I will share MCQ questions on real analysis, in WhatsApp group shortly. So I will stop here.